China's advancements in steel forging technology are setting new benchmarks, especially in stainless steel manufacturing. Precision engineering and innovative heat treatment methods to produce stainless steel of remarkable quality. These improvements are fueled by investments in high-tech equipment and research, allowing China to compete globally in high-performance steel products. In forging stainless steel, China utilizes cutting-edge techniques such as robotic-assisted forging and highly efficient, energy-saving induction heating. These technologies ensure uniform heating and precision, which are crucial for high-strength stainless steel components with intricate shapes. Advanced CNC machining and computer-controlled forging presses enable the production of stainless steel parts with extreme accuracy, from automotive and aerospace components to medical and food-grade equipment. Moreover, China's manufacturing facilities are increasingly eco-conscious, incorporating practices that reduce emissions and waste. With the integration of IoT and smart systems, real-time monitoring and predictive maintenance are now possible, which enhances production efficiency and reduces downtime. This approach optimizes the life cycle of forging equipment, enabling sustainable, high-volume production. The production begins with continuously cast round steel billets, each with a diameter of 230 millimeters. The majority of these continuously cast billets are cut to specific lengths using carbide-tipped saws, while a smaller percentage is preheated in a furnace before cutting. To prepare the billets for rolling, they are heated in an automated, computer-controlled rotary hearth furnace. This preheating process elevates the temperature of the billets to approximately 1,280 degrees Celsius, which is essential for the subsequent forming steps. Piercing process. Once the billets reach the desired temperature, they are fed into a D-sharp piercing mill. This system features rollers set at an angle to each other, which feed the heated billets over an internal piercer at a rate of 1 meter per second. This stage transforms the solid round billets into tube shells. To facilitate the formation of seamless pipes, mandrel bars are inserted into the pierced shells. The combination of the mandrel bar and tube shell is then pushed through a series of forming rolls, elongating the pierced shell up to 17 times its original length. The result is a hollow structure known as a hollow, which can measure up to 22 meters in length with a minimum wall thickness of 3 millimeters. Stretch reducing mill. The hollow, still containing the mandrel bar, is subsequently passed through a relay system where the rolls expand the hollow, allowing for the removal of the mandrel bar. Before entering the reheating furnace, the wall thickness of the hollow is monitored using a radiometric gauge, ensuring uniformity along its length. The hollows are then heated in a computer-controlled walking beam furnace, preparing them for the stretch reducing process. This step involves rotating the hollows as they pass through the furnace to ensure consistent heating. The final dimensions and wall thicknesses of the tubes are established in the stretch reducing mill, which consists of 28 stands. After the rolling process, the wall thicknesses are again verified using a radiometric gauge. The results are documented and displayed graphically, providing real-time data to control the rolling process. The tubes, now measuring up to 150 meters in length, undergo rapid cooling to achieve specific mechanical properties. Final processing. Once cooled, the tubes are cut to predetermined lengths using carbide-tipped saws. Depending on their intended application, the tubes may either undergo further processing or be sent as raw material for drying or drill pipe manufacturing. The seamless pipes produced cater to a wide array of industries, including automotive, oil and gas, and boiler manufacturing. When required, the tubes can be shipped with ends up set to meet API specifications. This involves heating the pipe ends to forging temperatures using induction heaters and subsequently upsetting them through mechanical or hydraulic upsetters. This process may involve up to 3 forming steps: heat treatment and testing. The next critical phase involves heat treatment. The pipes are heated in an austenitizing furnace, altering their microstructure to prepare them for hardening. Rapid cooling during the quenching process results in a defined microstructure that is both hard and strong. Following quenching, the pipes are tempered in a temper furnace to achieve the desired strength level. To ensure quality, each tube undergoes non-destructive testing. This includes electromagnetic inspections for wall thickness and surface flaws, followed by ultraviolet magnetic particle testing for pipe ends. The testing measures inner and outer surfaces for various types of flaws and ensures that all products meet strict quality standards. Threading and final inspection. The finished tubes are subjected to threading on CNC machines, which create connections ranging from basic API threads to advanced gas-tight premium connections. Couplings are produced from seamless tubes, with threads cut to precise specifications. Hydrostatic testing is performed to ensure the integrity of the pipes. This involves filling the tubes with an oil-water emulsion, pressurizing them, and holding the pressure to assess their durability. After testing, each threaded end is coated with corrosion-resistant grease and fitted with a protective cap. In the final steps, tubes are weighed and measured, stamped with unique identification numbers, and prepared for shipment. Each product is bundled and strapped securely, ready for delivery to clients. Alpina Tubulars continues to be a leader in seamless pipe production, combining advanced technology with stringent quality controls to meet the needs of various industries worldwide. In India, some steel production facilities continue to use primitive rolling mill technology, which relies heavily on manual labor. In these traditional setups, steel billets are prepared and manually transferred to the rolling mill, a process that requires a high degree of physical effort and skill from the workers. Typically, workers handle billets that have been preheated in a furnace. These heated billets are then manually positioned on a roller table or conveyor system, which feeds them into the rolling mill. The process requires precise timing and coordination, as the workers must quickly and carefully position each billet to ensure it feeds smoothly into the mill without delays. Even minor errors in alignment can disrupt production and potentially cause injury, highlighting the importance of experience and attention to detail in this work. Once in the rolling mill, the billet undergoes repeated passes through heavy rollers, gradually reducing its thickness to produce rods, bars, or other profiles as needed. In most advanced steel plants, this step is automated, but in facilities with primitive technology, it is managed manually, adding to the physical strain and prolonging the processing time. Despite the challenges, this manual approach to rolling steel remains common in smaller, cost-sensitive operations due to lower initial investment costs compared to automated alternatives. However, the reliance on human labor also leads to safety risks, lower productivity, and inconsistent product quality, making it difficult for these operations to remain competitive. While the industry is gradually moving toward modernization, the persistence of manual labor in rolling mills underscores the need for affordable automation solutions tailored to smaller facilities. The process begins with milling, where the raw material is shaped to approximate dimensions. Milling is followed by flute formation, a crucial step as the flutes allow chips to escape during threading. This step involves careful machining to create precise and symmetrical flutes that optimize chip flow and cutting performance. Heat treatment is then applied to harden the tap, ensuring it withstands high stress during use. This process enhances the tap's strength, wear resistance, and durability. Following heat treatment, grinding is carried out in multiple stages: grinding the square, for handling and alignment; grinding the flute, and then grinding the shank and edge. Each grinding stage refines the tap's shape and prepares it for threading. The threading process itself involves grinding the threads to precise dimensions, a step that ensures compatibility with the designated thread profile and enhances the tap's cutting efficiency. Afterward, the edge is ground to refine the cutting angle and improve the tap's penetration into material. A chamfer is then applied, which helps the tap engage smoothly with the material being threaded. To further improve tool life and reduce friction, a titanium nitride tin coating is applied. This golden-colored layer increases hardness and resists wear, especially in high-speed applications. Finally, laser marking is used to label the tap with critical specifications for easy identification. This precise, multi-step process ensures the production of high-quality thread taps capable of delivering reliable performance in various applications. Creating a Morse taper shank twist drill involves several precise and high-quality manufacturing processes to ensure durability, accuracy, and cutting efficiency. Here's a step-by-step overview. 1. Rolling and forging. The process starts with a rolling forged machine, where the raw material, typically high-speed steel, undergoes rolling and forging. This shapes the drill blank and aligns the grain structure, which is essential for strength and durability. 2. Cutting tips. Once the basic shape is formed, the next step is to machine the cutting tips. This is an important process as it directly influences the drill's ability to cut through materials effectively. 3. Grinding tips. Grinding the tips is a meticulous process where high-precision grinding tools refine the cutting edges, ensuring they're sharp and angled correctly. This step involves removing material carefully to achieve a tip profile that allows smooth entry into the material being drilled, improving overall performance and reducing wear. 4. Straightening. After forging, the drill blanks may have slight bends or warps, so they undergo a straightening process. This step ensures that each drill bit maintains precise alignment, critical for accurate drilling. 5. Lathe turning. The drill bit is then turned on a lathe to achieve a smooth, uniform shank. 6. Milling the tang. At the end of the shank, the tang is milled. This part ensures a secure fit within the taper socket by providing additional grip and preventing slipping during operation. 7. Snagging and polishing. After milling, any rough edges or burrs are removed through snagging, where high-speed grinding wheels smooth the surface. Polishing follows, which further refines the surface of the drill, giving it a smoother appearance and reducing friction when in use. 8. Heat treatment. This process typically involves heating the bits to high temperatures and then cooling them in a controlled manner, creating a tough, resilient tool suitable for high-speed drilling operations. 9. Accurate cylindrical grinding of the shank and edge. Accurate cylindrical grinding is then applied to both the shank and the cutting edge, ensuring tight tolerances and exact diameters. This step refines the tool's surface finish and ensures that the shank and edge meet precise dimensional standards, enhancing accuracy and performance. 10. Grinding the point. The point is ground to the desired shape, angle, and tip geometry, which affects the drill's penetration ability. Point grinding ensures the drill has the right characteristics for fast, smooth entry into materials and extends the lifespan of the tool. (11) Rolling mark and nitriding. The final steps involve applying the brand or rolling mark, in this case, Hey Go, and subjecting the drill to nitriding. Nitriding is a surface hardening process that makes the drill bit more wear-resistant and durable. This process enhances the tool's ability to withstand high temperatures and prolonged use without degrading. In aerospace manufacturing, the Heller HF3500 is utilized for precision machining of components like the torsion link, a crucial part of an aircraft's main landing gear. This component, made from high-strength aluminum alloy NA7075, ALSNAM GCU 1.5, helps prevent the cylinder rod from twisting within the housing. Using the Heller HF3500 equipped with the District of Columbia 63I spindle and Pro package, machining begins with roughing passes using edge milling cutters, O63 at 1,300 meters per minute, O32 at 1,600 meters per minute, to efficiently remove bulk material. A O20 cutter then performs finishing at 1,000 meters per minute, achieving precise dimensions and surface quality. Heller partners with Walter for tool solutions, ensuring high-quality performance for aerospace standards. The HF3500's capability for fast, reliable aluminum machining makes it ideal for producing critical, lightweight aircraft parts. The Heller H10000 Machining Center, equipped with the XPC 100 spindle, XHD tool changer, and chain-type tool magazine, provides high flexibility and efficiency in tool management and machining. With an automatic tool change system, the Heller PDK-80 tool can be swapped directly from the magazine, reducing setup time and costs. This system allows for efficient front-end tool changes into a universal facing head, eliminating the need for multiple heads. An NC axis enables precise radial tool actuation for complex internal and external geometries. The design minimizes magazine space requirements, as only one facing head is needed for multiple front-end tools. Additionally, the machine ensures high rigidity, supported by a 160 mm diameter flat contact surface, enhancing machining accuracy and stability. For Far Eastern drilling, the production process of tricone roller cone bits follows precise steps to ensure durability and efficiency in various drilling applications, including water well drilling and mineral exploration. Each tricone bit comprises 3 cones, with each cone undergoing specific stages like rough turning the spindle nose, which sets the foundation for subsequent processing. The semi-finishing and fine turning of the 120 degrees phase further improve bearing capacity and working life, crucial for long-term performance under tough rock conditions. The spindle nose is refined through fine ornithic finishing for smooth operation and reduced wear. To enhance the bit's adaptability to different rock formations, the manufacturing process includes carburizing, hardening the surface for greater cutting efficiency. The teeth and inserts can be tailored in size, material, and structure to suit the unique requirements of each drilling scenario. Additionally, the bit's internal structure incorporates a Shatia bug diversion chute and a pin plug hole to improve chip evacuation and prevent bearing failures. These combined innovations enable Far Eastern Drilling's tricone bits to perform reliably across diverse mining environments. Virel manufactures drill bits using advanced technology and specialized processes designed for durability and efficiency in drilling. Their production includes precision-engineered fixed cutter and roller cone bits, with body materials and cutting structures customized to specific applications. Virel utilizes proprietary software for optimized design and advanced CNC machinery for high-accuracy shaping. Heat treatment further strengthens each bit, enhancing wear resistance and lifespan. In-house testing compares PDC and tungsten carbide cutters to ensure quality and performance. Emirates Steel Industries, ESI, in Abu Dhabi operates an advanced 1.4 million tons per year, MTPY, direct reduced iron, dry, based mini-mall, designed for the efficient production of heavy steel sections. This facility integrates cutting-edge technologies across multiple production stages to ensure quality and productivity. The plant's operations begin with a 1.6 MTPY direct reduction plant, which converts iron ore into direct reduced iron, dry. This dry is a primary input for the electric arc furnace, EAF, reducing dependency on scrap and helping ESI achieve consistent steel quality and sustainable practices. The dry is fed into a high-capacity, 150-ton fast arc electric arc furnace, known for its fast melting rates and energy efficiency. This furnace combines electrical and chemical energy to melt the dry, producing molten steel at high temperatures. After melting, the steel is refined further in a 150-ton ladle furnace featuring an inert roof, allowing precise control over temperature and chemical composition. This refining process ensures the steel meets the strict specifications required for heavy sections used in construction and infrastructure. Once refined, the steel is cast using the fast cast continuous casting technology. The plant's 5-strand fast cast conticaster has been specifically designed to cast billets, blooms, and beam blanks. This casting method enables continuous production and precise shape formation, setting a strong foundation for the subsequent heavy section rolling process. The heavy section mill is the final production stage, where the cast blooms and beam blanks are rolled into parallel flange beams, columns, and bearing piles. This mill has the flexibility to produce various structural sections, which are essential for large-scale construction projects, from skyscrapers to industrial plants. The parallel flange beams and columns provide high structural integrity and are in high demand within the regional and international markets. Bearing piles are also produced, serving foundational requirements for buildings and other heavy structures. ESI's mini-mall design ensures efficient use of raw materials, energy, and human resources. The integration of direct reduction, advanced electric arc furnace technology, ladle furnace refinement, continuous casting, and specialized heavy section rolling aligns with global sustainability goals. This approach allows ESI to produce high-quality heavy steel sections while minimizing waste and emissions, supporting the UAE's industrial growth and infrastructure development with a focus on environmental responsibility.